right, good morning, everyone. Today we're going to continue our discussion about the generalized central limit theorem for non-independent sequences. So now that our variables in the sequence are still identically distributed, but they are no longer independent. So to just give you a recap, we basically made two important assumptions for the special dependence we're going to deal with here. So the first one is stationary. And the second is M-dependent. So with those two important assumptions, what we can actually derive is that for the variance of the sample mean, we have this important formula. The variance of x and bar, which we derived last time, can actually be written as sigma squared over m. I'll define the notation soon, but let's write it down first. So sigma squared over m plus 2 over n squared times a summation where k goes from 1 to n minus 1 and n minus k times gamma k. Okay, so we only need two, I would say two. We only need the parameter sigma square, gamma 1 to gamma n minus 1. So that's the general formula, right? But here we can cap it at m. So because of the m dependence, let me see my red pen. Okay, never mind. So basically this one, because of the m dependence, we can write it as m. So we just need sigma square gamma 1 to gamma m. So how do we define those? Sigma square is defined as the variance of xi. And because they're IID, we can write this just as the variance of x1. Let me zoom in a little bit. Okay, and gamma k, let's just call this gamma j. Or gamma k, yeah, just to be consistent. Gamma k is defined as the covariance of xi and xi plus k. So they are apart from each other by k in the sequence. And again, because of the stationarity, this is actually equal to covariance of x1 to x1 plus k. So this is because of the stationarity. So you see that this can give us a lot more convenience for computing this gamma k. So in other words, this variance of x and bar is only depending on sigma squared, gamma 1 to gamma m. As long as we can calculate those, we can calculate the variance of x and bar. And we'll see soon that we can have the asymptotic version of something like this. So this is the root n, the formula we're familiar with, root n times xn bar minus mu, okay? Where mu is defined as the mean or expectation of xi. Of course, it's expectation of x1. So this quantity is what we're mostly interested in for the asymptotic distribution, just as for central limit theorem. So we're going to show this thing will converge to an asymptotic normal distribution. But before doing that, we want to get a sense of what's its variance. Right, before we talk about the distribution of its asymptotic distribution, we first calculate variance to get us a basic sense. So last time we derived this, right, based on this. So basically the shift by mu doesn't change variance at all. And this multiplication by root n would multiply the variance by n. So that's why this variance becomes sigma squared plus 2 over n, right? We have this summation k from 1 to n minus k, gamma k. So as long as we can show that this term converges to a constant, then this term will have a variance convergent to a constant. So that's what's needed for us. Okay, so because of the summation only go from 1 to n, we can move this n inside, right? The summation term has nothing to do with n. So for the second term, this one, we can write it as 2 times k go from 1 to n minus k over n times gamma k. Now asymptotically, we have an easy limit because n minus k over n, we know k is bounded from n. So this term is convergent to 1. So we would have this converging as our n go to infinity to 2 times k from 1 to n gamma k. That's it. So we have shown the limit of the variance of this term, asymptotic variance. So now the remaining question is, do we have asymptotic normality? So what's left for us is to answer this question. Does this convergent law to normal distribution with mean 0 and asymptotic variance as sigma squared plus 2 times sum k from 1 to n gamma k? Okay, so what's left for us is this asymptotic normality. And that's what we're going to show next. Okay, before we talk about the theorem regarding this conclusion, I'm going to give some important obviously hint or discussion about your homework problem regarding the convergence in quadratic mean. That is something I got questions about. So essentially, for the convergence in quadratic mean, it is related to what we said, the convergence in the, is the same as the convergence in the rth mean with r equals 2. That's a note we posted in the front of the homework. And then what you're gonna show for convergence in quadratic mean, essentially, if you're trying to show, I'm just going to say this is a side note, right? So if you're going to show something like for an estimator, right? So if we have an estimator, basically, theta hat n, and if we have a parameter theta, okay? So this is an estimator. This is a parameter, okay? Then if you have the expectation of the estimator equal to the parameter, suppose you have that, then if you want to show that theta hat n converges in quadratic mean to theta, if that's something you want to show, then you basically just need to show, it is equivalent to show that the variance of theta hat n goes down to 0 as n go to infinity. So it's basically by definition, that's it, right? Because if the theta is its expectation, then the expectation of theta hat n minus theta squared, that term is the definition of the variance. So you just need to show the variance go down to 0 as n go to infinity. So in that case, if you can have a closed form formula for the variance, then you can see whether that variance formula goes down to 0 as n go to infinity. That's a very simple way to deal with the problem like this. And so also, whenever we have this, right, we have a very nice result because it's in statistics. This is regarding whether the estimator has a mean squared error converging to 0. And that's a good property about the estimator. Okay. And also with this, we can further show the estimator's convergence to theta in probability. We basically can deal with this using the Chebyshev's inequality. And also we have that implication already. So in our earlier lecture, we said that convergence in the rth mean for any r implies the convergence in probability, right? We have the almost sure convergence implies convergence in probability. We also have the convergence in Rth mean implies convergence in probability. So those are natural results to obtain. Okay, so now let's come back to our theme, the theorem regarding this important result. Okay, I already have the statement. So theorem. We have conditions, two conditions regarding stationarity and M dependence. Okay, so for some M greater or equal than 0, so you can consider M to be fixed. And we have x1, x2, and so on is a stationary M dependent sequence with expectation of each xi equal to mu and variance of each xi being finite, constant and finite. The same condition we need for central limit theorem. Then we have this statement. I'm going to copy it once more. Xn bar minus mu converges in law to normal distribution, zero mean, variance. That's it. Very simple and elegant conclusion. Compared to central limit theorem, we basically only have this additional term that is due to the covariance structure, right? Because we know the covariance structure only happens for between variable pairs that are less than distance m from each other. So that's why this term just go to m, it doesn't go any further. Because say x1 and x1 plus m has no more, x1 and x1 plus m plus 1 has no more dependence. So those long-term dependence can be ignored. Okay, so how do we prove this? Actually, this proof has a lot of interest intuition, which I want to talk about. So the intuition is actually this. So let's say that I have my sequence, okay, x1, x2, and so on. And let's say xm, xm plus 1, and so on. So what I'm trying to look at is that I first consider n to be fixed, okay? So basically, I look at this part. And then I allow my n to go to infinity. But for now, I consider my n to be fixed. And what's more, what I want to do is that I want to define, I want to fix. So first fix n, and then I fix a constant k. So k is basically a segment, let's say x1, x2 to xk. Something here. And this is a sequence, subsequence, which I can allow k to grow as well. But k is nested under n. And then I want to arbitrarily introduce a gap of length m in the middle. So you see, this is a length k subsequence. And then I want to introduce a gap here of length m. So together, this will be a length k plus n. And what I want to do is that I want to divide my sequence length n into pieces of length k plus n. So what I'm going to do is that I will do, this is k plus m, this is another k plus m, and so on. Okay, so I'll see how many segments of k plus m I can divide. So essentially, by this idea, maybe I can rewrite it here, okay? So let's say this is a length m, and I'm going to divide it into k plus m, and so on. And here, probably this is the last k plus m. And what's left here, I call a remainder of length r. So essentially, I can write n equals to s times k plus m plus r. So what I would have is that since r is a remainder, so I would have r being non-negative, but less than k plus m. Otherwise, I could cut this another segment, right? So the remainder must be less than the segment length. And s is basically the number of segments I could have. So then this s is basically the floor of n divided by k plus m. I'm taking the floor integer of this ratio. And you see the benefit of doing this is that I want to introduce some independence into my derivation. And I want then with independence, I can make use of the central limit theorem. So that's the basic idea of why I'm going to do this. Okay, so essentially, you see, within this segment, I can further call the first k as here, and then I have m, and then I have k, I have m, and I can do that for every segment. So why do I want to do this? The reason is that if you think about the m dependence, we know that by looking at the variables here and the variables here, because they are separated by m, then each pair of variables, one from each segment, will be independent of each other. So therefore, if I take a partial sum here and a partial sum here, these two partial sums will be independent. And that's what I want to say. So basically, I can rewrite the summation of x1 to xn. Don't forget the whole length is m, okay? So I can write the summation of xi, I from 1 to m, into 3 parts, okay? The first part is that I'm going to write the partial sum here. I have how many of them? I have s of them, right? I have s segments. So that partial sum will be the first part of my summation. And I will also have s partial sums from those m segments. I will have a partial sum here, here, and here, s of them. That's the second part. And the third part is the remainder. And adding them up, I can get my summation. So in other words, I can rewrite this part as the summation. Okay, I'm going to introduce some more notation so you can connect with my notes. So I let s go from, I let j go from 0 to s minus 1. So basically, I'm just introducing 0, starting from 0 index, okay? 0 to s minus 1, just to be consistent with the notes. But you can change it to j go from 1 to s. That doesn't matter that much. And here, I define the partial sum for this one as the vkj. Okay, the reason I have k here is k indicates the length of this segment, and that's something I can vary. I arbitrarily set k. So that's why k must be here. And j is to indicate the number or which segment you're referring to, right? I have 0, 1, 2, s minus 1. That's the first part. The second part is regarding the m segments partial sum. So I can write this as, again, j from 0 to s minus 1, wkj. Okay, that's regarding those partial sum. And the last part, I can write it as I from 1 to r. That's the last segment. And it's actually x times, s of the index s times k plus m plus I. You see, I'm just getting the index of the elements here. Okay, so where you see the VKJ is the partial sum of the K length segments. So it's I from 1 to K, and it's xj K plus M plus I. You see now the reason why we want to J start from 0, because that can help us write down the first segment easily, right? The first segment J is 0 and I go from 1 to K. If I let J start from 1, then here will be J minus 1. That's why. And WKJ, still I let I go from now K plus 1 to K plus M, right? That's the second part of the segment. And here I have X, J times K plus M plus I. That's it. So to prove the asymptotic normality, you see what I can make use of is the independence of the VKJ for different J. Because let's say VK1, that's here, and VK2, that's here. These two partial sums are independent of each other. So for this part, I can let it have asymptotic normality if I let S go to infinity, right? So here, 1 partial sum, 2 partial sum, S partial sum. If I fix K, but let N go to infinity, what happens is that, so look at here, if I fix K, but let N go to infinity, then S will go to infinity. Then for this summation, I can use central limit theorem to get an asymptotic normality. For this part, you see, this part and this part, I cannot. But my hope is that since ultimately I want to divide the summation here by n. So my hope is that this part divided by n and this part divided by m will go down to 0. So that's my hope. So that's why my asymptotic distribution of this part will be dominated by this part. Then I'm done. Okay, so you can imagine under what case will this be dominated by this? First of all, let n go to infinity and let k go to infinity. Then you see that compared to n, the proportion of m is negligible, right? N over m over n is a very, very small part of the summation. So it's the remainder. When that happens, then I can approximate basically this part by this part, and I'm done. Okay, so before we actually do it, let's get a very important lemma, which is something we needed to show the proof. So let's defer this a little bit, and let's first talk about lemma. So the lemma uses different set of notation, so I don't want us to get confused. So let's pay a little more attention to the lemma. And this lemma is actually about what we need for that proof. So Tn is something we want to prove the asymptotic, want to derive the asymptotic distribution. We write Tn into two parts, z and k plus x and k. So you see, we introduce another notation or another subscript k. So here n go from 1 to infinity, so is k. Okay, so then we want to have some interesting conditions and then a result. So if these three conditions hold, first of all, x and k, this term, converges in probability to 0 uniformly in n as k goes to infinity. Okay, what does this mean? This is similar to what we talk about uniform convergence or uniform limit, right? Uniform convergence is applied here. So what this means is that, so when k goes to infinity, you just worry about k. Then regardless of n, this always goes to 0. And this means what? If you think about the definition of convergence and probability, it is actually, maybe I can write a little bit more. So what this means is that, so the definition is for any epsilon greater than 0, right? This means that the probability of x and k minus 0 greater than epsilon, this is convergent to 0 as k goes to infinity. That's the definition of convergence and probability. Then how about the uniform in k? Then we need to make use of the definition for this convergence, right? The convergence of real numbers, right? The probability is a real number. So what this means is that for any delta greater than 0, there exists a k, and this k has nothing to do with n. Exists a k which is an integer, okay? Such that we would have the probability of this x and k, I can ignore the minus 0, greater than epsilon, less than delta for all small k greater or equal than big K. That's it. So I'm just using the definition of a limit. And here a uniform in n means that this integer big K has nothing to do with n. And in other words, this is holding for all the n. So this has nothing to do, it's irrelevant to n. So therefore, this is for all such K, and of course, for all n. This is what we mean by uniform convergence. So in other words, the first condition is only about the consequence when K go to infinity, and it doesn't depend on n. That's the first condition. The second condition is about this term, Z and K. So since we have two sub-index, we want to talk about how each one changes and what happens. So here we have a two-step convergence in law for Z and K. So first of all, we have Z and K converge in law to ZK. Okay, so maybe I'll put this. Z and K converge in law to ZK as n go to infinity for each K. You see, here I'm not saying uniform for K, but for each K, because the limit is still depending on K. So I'm only getting rid of n by letting n go to infinity, but K stays here. And then I can have Z and K, ZK, this limit, converge in law to Z as K go to infinity. So I'm saying that this is a two-step convergence in law. By letting n go to infinity, I can have a limiting random variable whose distribution is the asymptotic distribution for Z and K when n is infinity. And this ZK itself still depends on K. Next, I let K go to infinity further, and I have a limit, random variable, limiting random variable, and here this limit has nothing to do with both K and n. So with these three combined together, then I can have Tn converge in law to the final limit Z as n go to infinity. So see, what's special about this lemma is that what we want to prove is only about n. But what we use in the middle is by arbitrarily introducing another index K and let K change. So you see, this is a proof for convenience. That is, if we can easily prove this, this, and this, those three conditions, then we can finally prove the target. That is the asymptotic distribution of Tn in terms of n. And why this is related to our theorem is because if you think about it, here, my target is only about n, but when I decompose it into 3 terms, you see the terms involve k, and k is what I arbitrarily introduced. And ultimately, I want n go to infinity and want k to go to infinity. And that's exactly the context of my lemma. So that's why the lemma is here for the purpose of proving this theorem. But I think this is a very useful technique because by introducing a intermediate sub-index, if you can make the proof of 1, 2, 3 more easily, then you can prove your conclusion more easily. So I'm not going to talk about the proof of the lemma. You can check it in the notes. It's based on the definition of convergence and law, and that's it. Right. So we're also going to use this convergence probability in the middle, but that's basically what we want to show. It's about it's a proof based on the definitions of convergence in law and convergence in probability. So but we're going to use this lemma for helping us to prove that theorem. Okay, so just to simplify our notation a little more, so coming back to the theorem. So back to this theorem, I'm going to introduce some notations to help us. Okay, so I'm going to, maybe I will simplify things a little bit so that I'm not going to stick with the notations in the notes, because I think the notes we have another set of intermediate notations which complicated things a little bit, but I'll just stick with these raw notations here and the notations in my lemma. Okay, so you know what I'm going to show is that, so without loss of generality, right? This is a very common technique. Without loss of generality, we assume mu equals 0. So in other words, we assume each random variable is centered at 0. That's totally okay because we're going to subtract the mean anyway. So this is fine. And then you see, we can write, right? So then our target, this root n times xm bar minus mu, can just be written as this summation xi, I from 1 to n divided by root n. Okay, that's it. This is something I want to prove for its asymptotic distribution. I want to show. And then that's the target, my Tn, right? Tn is something I want to derive asymptotic distribution. So I just define Tn to be equal to that. So define Tn to be equal to summation xi, I from 1 to n over root n. That's my Tn and my target. How about these parts, right? This part, and this part. So since I'm dividing the left-hand side by root n, I need to divide by this term by root n, this term by root n, and this term by root n. Okay, so you see in my lemma, I only have 2 terms, right? In my lemma, I only have z and k and x and k. But here, I have 3 terms. Okay, so what I'm gonna do is I will actually shuffle them a little bit. I will combine this one with this one, call them as my first term, this as my second term. The reason is actually, if you think about it, this term has nothing to do with k. K is just a symbol here. What it's actually about by the stationarity is I take summation of r random variables in the last part of my sequence, right? So k is what is k doesn't matter that much. So what I do is that I combine this summation with this summation as my z and k. So define z and k, okay? as the root n, oops, where I have summation j from 0 to s minus 1, vkj plus I from 1 to r, x is k plus m plus I. That's my second term. And my third term, which I call x and k in the lemma, would be root n. And here is j from 0 to s minus 1, wkj. That's it.
Excuse me, Professor?
Yeah. Yeah.
Can you please just move the paper a little bit to the right?
To the right. Okay.
I think so. Yeah.
Okay.
Maybe even a tiny bit more if possible. Okay, great.
Okay. So, yep. So then you see by this definition, I would have Tm equals z and k plus x and k. Okay, so I'm in the setting of my lemma. Then I just want to show what's in the lemma. So I want to show x and k converge to 0 in probability as k go to infinity uniform for m. That's condition 1 in the lemma. Second, I want to show that as n go to infinity, z and k is converging in law to zk. That's condition 2 of the lemma. Third, I want to show zk is convergent to an asymptotic distribution as k go to infinity. That's condition 3 of the lemma. So I'm going to show that each of those would hold. Okay, so first of all, we want to look at this. Maybe let's look at condition 1. Okay, so let's think about what's the variance of this x and k. So let's check. Okay, I can move this away. That will be easier. So first of all, let's check condition 1 of lemma. And that's about x and k, okay? So I want to show x and k converge into 0 in probability. As I said, an easy way to prove it is to show the variance going down to 0. Okay, so since, if you think about it, the expectation of x and k, which is what? Is actually here. It's basically the expectation of wkj, okay? And what's wkj? It's a partial sum. So I can further write it as, okay, and I go from k plus 1 to k plus m. It's the second half of the segment k plus m, right? We are looking at the second half, that's length m. Expectation xj k plus m plus I, right? Now we are in mean 0 situation. So this is 0. So we just need to show it is sufficient to show that the variance of x and k is going down to 0 as k go to infinity and uniformly in n. That's enough. If we can show this, then we can already have convergence in probability. Okay, then what's the variance of x and k? So by our definition like this, then you can clearly see we already write it out, right? So basically you see that for the WKJ, so here we have J go from 0 to S plus 1. And that's what? It's actually, if we can allow K, because K is going to infinity. Okay, I'll put my first piece of paper back. Look at this graph. So K can be very, very large, right? When K is very large, then this segment and this segment, they will be apart by K. And for sure, I can let K greater than M. So then this part and this part will be independent of each other. So I will have independent partial sums here, here to here, S of them. So that's why, you see, when I can when K is large, right? When K is greater than M, then the variance of this is essentially, I can write 1 over M, and it becomes the summation of variance of WKJ. And since J go from 0 to S minus 1, there are S of them, and they have the identical variance, then essentially I can say this is equal to M minus 1 over N times S times the variance of WK0, okay? Because they have the same variance. And WK0 is what? So I can further write it out as over M times the variance of a summation. That's actually, so J is now 0. It's actually I go from K plus 1 to K plus M, Xi. Okay? Summation of M subsequent random variables. And
Excuse me,
actually, yeah.
Sorry to interrupt. I'm just wondering, on the homework we proved Bernstein's theorem. If we would that show this part that the variance of x sub nk goes to 0? Okay. Okay.
Right. So we're going to show that actually.
But if we could just cite Bernstein's theorem, would that like finish this small part of the proof?
If you have that, you know that, then you can directly use it. But here we're just pretending we don't know it. So that's why we're deriving it. Yeah. Because we didn't actually teach it as a result in the lecture. We just treat it as an exercise for you guys to prove it. Yeah. So then you see that here we have how many of them? M of them, right? M of xi's adding up. And we have this variance formula already. So that's actually equal to S over M times, okay, I have this as, this part as the M times sigma square, right? M of them. And also, I have the 2 times K from 1 to M. And that's gamma K. Okay, I have the covariance of each of them, of the pairs within here. I think that's it, right? So for this part, what I need to show is that, so here, this is a constant, I know. It doesn't change, right? It's a constant, but for this part, it's actually bounded by what? So S over M, don't forget that S is the number of segments and N is the total length. So I know this actually depends on K, right? Because I have this important result. That is N is equal to S times this plus R. So if I divide S to this side, then you can see, because I have N divided by S, right? This is greater than k plus m. I do have this. So then I would have s over n is less than 1 plus k plus 1 over k plus m. And this is less than 1 over k. So that's why with this result, the variance here will be less than 1 over k times the constant. And that's why if I let k go to infinity, now you see n is away. I don't have n here anymore. That's why here, if I let k go to infinity, this is going to 0. And that's exactly why I have condition 1 satisfied. So I'm done with this part. So this part is handled. Now I need to worry about this part, the z and k. And here, what is z and k? Z and k has 2 parts. The partial sum for segments of length k and the remainder. Okay, I need to deal with each one separately. And what I will do is that I will first let n go to infinity. That's for condition 2. And I'll let k go to infinity. That's for condition 3. Okay, so let's first look at the remainder term. So we will deal with that first. So in z and k, so the first part is this. For the remainder, I from 1 to r s okay, this one. And what I would have is, again, for this term, its expectation for sure is 0, right? We have center, mean, random variables. How about variance? Right? And we know it's actually by stationarity. It's basically equal to the variance of xi, I from 1 to r, root m, right? No matter where this segment is at, whether in the beginning or in the last, it have the same variance. So that's why you see I can get it out, right? I can get this root n out, and it becomes the variance of that. Then by the same argument we have before, just now, this is r times sigma squared plus 2 times, okay, k from 1 to r minus 1. R is less than, we don't know actually. Yeah, so we don't know if r is less than m or not, because we know r is less than k plus m. So I'll just do this. K from 1 to m, gamma k. So still, I can give it the upper bound here. And then you see what's happening. Here, this term is only related to m. Okay, this is a constant and this is a constant, right? So what happens here is, oh, sorry, not a constant. I know r is less than, because r is less than k plus m. Right, this is the condition for remainder. Then what I can say is, right, what I can say here is that, okay, so for each of them, let me see, k plus m sigma squared. Right, okay, my bad. Yeah, so I'm actually being a little bit ambitious here. But here, what I'm saying here is that the r is bounded by k plus m. If I fix k, okay? If I fix k, then what's only going to infinity is m. So I don't need to worry about k anymore. So then this one, as n go to infinity, will go down to 0, right? Because I have a fixed k, then this becomes a constant, then I'm good. So in other words, for this term, if I only worry about m, I can have the remainder going to 0. Then in zk, you see, I only have another term to deal with. Let me write it down. Write it out again. So if you recall, our z and k has two terms. One is j go from 0 to s minus 1, vkj. And the second term is what I write here, I from 1 to r, sk. Okay, I have this term. And now I only worry about n, right? That's the condition 2. Condition 2 of the lemma, I only worry about n, not k. So with k fixed, here I already showed that this part is converging to 0 in probability because of this. If I have variance going to 0, I have the convergence in 0 to probability, to 0 in probability. Then only about this part. And this part, you know, is exactly where I can apply central limit theorem. So you see, when I let k fixed, when I let n go to infinity, then s will go to infinity. S is the number of segments, right? So if each segment of length k plus n is fixed, then the number of segments will go to infinity. So this part, I can apply the central limit theorem. And what is that? You know, if I let n go to infinity, then this is actually implies s go to infinity. Then by central limit theorem, I can have this part converge in law to a normal distribution, okay, with mean 0 and some variance. So that's why I'm quite happy about this part. But this is just the idea. I need to write it out further. Okay, so by central limit theorem, essentially, you see, central limit theorem is about the summation of s segments with s going to infinity. So the central limit theorem statement should look like this. Root s times the summation j from 0 to s minus 1, vkj divided by s, right? This is the average minus its mean 0. This will converge in law to normal mean 0. And the variance would be the variance of each vkj. And that will be the variance of, let's write vk0. That's the central limit theorem result. And here again, because we have independence, since the vkj's are apart from each other by n in the sequence. Then what's vk0? Where the variance of vk0, if we think about it, it's basically the variance of the summation of the first k random variables, xi, I from 1 to k, right? And we know here, we can use that formula again for the variance of the summation. So we have it as equal to k times sigma squared, right? K of them. And also we have the covariance term. So as here, we can assume k to be larger than m, okay? K large. So then we can have all the m dependencies here. I would have 2 times the summation j from 1 to m gamma j. So still have those covariance terms here. That's it. So therefore, you see, I do have the variance here fixed by k, and here the covariance term, right? Then what's left for my root n? So this is about the this is about the root. So if I do this, I can actually show that this left-hand side is about, okay, summation vkj, j from 0 to s minus 1 over root s. I'm simplifying the left-hand side, converge in law to normal, 0 mean, and the variance is k sigma square plus 2 times j from 1 to m gamma j. And I need to deal with root n. So I have a swap from root n to root s. However, that's not a real problem because, why is that? Let me see if I missed something. I think I might have missed something here. It's k times sigma square. Vk0 is the partial sum. Right. Vk, okay. Right, so this is the partial, each term is the partial sum. So the variance is about the partial sum, right? So the variance should be this, k of them, and sigma square, and this. Oh, I think I might have missed something here. Right, I think I missed something here. I think this term is not right. So essentially, when we have the covariance part, we have the summation. So j go from 1 to m. Here, I think I missed this. So this should be k minus j and gamma j. Yeah, I missed this term here. Okay, that's the thing I need. And so coming back to here, right? So here I need to change the denominator from root s to root n. But now as I have the k plus m as fixed, so since you see, I'm going to write this again. Since n equals s times k plus m plus r. And then, so with this and with k fixed, right? So I can have the, so when n goes to infinity, then as I said, s will go to infinity, the remainder is no longer mattering. So I have the s over m will converge, as n go to infinity, will converge to 1 over k plus m. So I would have that. So that's why if I multiply, you see, so then this summation vkj, j from 0 to s minus 1, root n, can be written as root n, root s divided by root n times this. Right? So I have this. Then its variance or its asymptotic distribution is just a scaled version of this. And this limit is convergent to 1 over, this thing is convergent to 1 over root k plus m. And this root k plus m will be squared before they enter the covariance. So here, sorry, I think this thing also need to be changed. So I need to have k minus j here.
Wait, Professor?
Yep.
Can you explain again why if there's a k minus j there?
The reason is because if I go back to this page, the reason is we have n minus k here, you see.
Oh, got it. Thank you.
Yeah. So that's why we have summation of k terms. Don't forget about this. I made a mistake myself. So I have k copies of the variance, and in the covariance, if I'm taking the summation by the gap, then don't forget this k minus j here. Yeah. So that's why you see I can actually have the asymptotic distribution. So this one will converge in law to this one, but I need to scale the variance, okay? This is it. But for the variance, I need to scale by the square of that. And the limit of the square is the 1 over k plus n squared, right? So yes, 1 over k plus n. So basically, I need to have this k plus m. And then I have k sigma squared plus 2 times j from 1 to m, k minus j, gamma j. Okay? That's it. So you see, this is basically my limit for z and k. So it's a long argument, but if we go back here, z and k has 2 terms. And this term goes to 0 as k go to infinity, as n go to infinity, And this term, as n go to infinity, is going to this term. Okay, so k is fixed. I'm letting n go to infinity. Then I have this. So to summarize, I have z and k as n go to infinity converge in law to this. Okay, so I'm going to copy it again. Plus 2 times j from 0, 1 to m. So k minus j sigma j over k plus m. So k is still fixed. Now, finally, I'm going to let k go to infinity and see what happens. When k go to infinity, you see, m can be dropped, right? M is a constant, not comparable to k. So for the variance, the first term becomes sigma squared. And k plus m can go to the summation, k minus j over k plus n, going to 1. So I'm left with summation 2 j from 1 to m, gamma j. That's it. So basically, if we think about the lemma, this step is about 2, this step is about 3. And we're done. So finally, we prove the condition in the statement in the theorem. So this is a quite long argument. I hope you're still with me. But basically, the key idea, if you revisit everything, is about decomposing the summation into 3 parts in the beginning. And the first part is the partial sum of length k. And each partial sum is a part by m, so they are independent. That's why we can apply central limit theorem. That's it. And the second part is the partial sum of length m, and that is separated by k. Since k can be super large, these terms can be considered independent as well. And okay, sorry, it's here. It's here, right? So that's the check condition 1. So the partial sum of length m, and they are separated by gap k. And since k can be very large, can be larger than m, so I can have them independent. And because their summation, in each summation there are only n of them, and m is a fixed constant. The key is m is a fixed constant. So that's why compared to the increase in m, this is negligible. That's why we have the second part converge to 0 in probability. We don't worry about it. And the third part is the remainder, which we put into z and k in the lemma. And for the remainder, because it's only a summation of r random variables, And R is actually constrained, right? R is constrained by K plus M. It cannot be larger than that. And also we'll only have one R, right? One segment in the last. So comparing to the increasing M, this one's also negligible. So ultimately our summation x1 to xn is dominated by the sum of the partial sum of length K. And because the K can be very, very large, we can have them occupy the summation. And that's why ultimately we can apply the central limit theorem. So I think the smart thing here is that we fix the M, the gap, which is by the M dependent sequence, but we let the segment K to grow with M. But the trick in the proof is that when we apply the central limit theorem, we fix the K as a constant, just a large constant. And ultimately, once we deal with M, right, this is a central limit theorem result. Once we have N gone, we let K go to infinity finally, and we have the result. So I think the key argument here is that we introduce some intermediate index or number K to help us apply the central limit theorem. And ultimately, we let K go to infinity, and that satisfies our purpose. So I hope you think this theorem is quite enlightening in terms of the thought process. Still, I think at least a take-home message, if you ignore the technical details at all, so the take-home message is that central limit theorem is still the key. We make use of that to derive the asymptotic normality. And the trick is to introduce that intermediate number K. Okay, so that's all about the proof of the theorem. It took most of the class for today. But we're going to show, before we finish, I think I can show one application of the example. And this is more important for those of us who are interested in using the theorem. Okay, so I'll quickly do one example. Example 1. So in this example, we're going to look at, okay, I have this x1, x2, and so on, IID. And what I'm interested in is the summation. I from 1 to n, xi times xi plus n. So I'm interested in the product of two IID apart from each other by m, right? So this is called, actually has a name, it's called mth product moment. And if I'm interested in this asymptotic distribution, then I'm not having IID here, right? Clear, why is that? In the summation, because you see, in the summation, I will have x1 plus n. And I can also have a term x1 plus n times x1 plus 2n. So if they share x1 plus n, then they are not independent. So if both terms appear together, right? So if 1 plus n is less than n, then both terms will appear in my summation for Sn. So that's why I cannot simply assume they are independent, and I cannot simply apply central limit theorem. So what I'm going to do. So basically, to address the asymptotic distribution of Sn, right? This is the question I'm going to answer. What I can do is that I introduce a notation yi. I define it as xi times xi plus n, and I go from 1 to etc. I introduce this yi. And then I want to get the variance of yi and the covariance of yi and yi plus something. Okay, so variance of yi, right? I can just simply write it as the variance of y1. It's straightforward. It's the variance of x1 times x1 plus m. And by the definition of variance, I can write it as the expectation of x1 squared, x1 plus m squared, minus the square of expectation of x1 times x1 plus m. I can write it this way. And now I can use the independence of x1 and x1 plus m. By independence, this one can be written as expectation of x1 squared times expectation of x1 plus m squared. And so I should say IID. Then I can say this is expectation of x1 squared. Here is actually minus expectation of x1 to the fourth. Okay, square here and square here. What is that? So I didn't tell you the notation here. Maybe I should make it up. So expectation of xi, let's say, is equal to mu. And I say expectation of variance of xi, I call it tau square. We just use a different notation here, mu and tau square. Then you see this one, the first term, I know it's equal to mu square plus tau square, right? This is the definition based on variance plus expectation square. And this is equal to mu to the fourth. Okay, that's the variance I would have over here. So a little simplification can tell me this is equal to tau to the fourth plus 2 times tau squared mu squared, right? I have the variance. How about the covariance? So if you think about it, right, my y1 and y2, so y1, y2, 2, yn, y1 plus n, and so on. So if you think about this sequence, by the definition of y1, so this is x1, x1 plus m, this is x2 times x2 plus m, and here it's x1 plus m, x1 plus 2m. So you see, we only encounter the same random variable here, but nothing in the middle or nothing afterwards. So in other words, you see about my dependence here, I only have dependence when two yi's are apart by m. So that can simplify my question a lot. You see here, I have basically m dependence. But if I had look at y gamma 1, y1, y2, their dependence is 0. Their covariance is 0. And y1, y3, also 0. Gamma 2 is 0. And I only have a non-zero one when they are apart by m. So I only have gamma 0 as the only non-zero one. So you see gamma m minus 1 is also 0. How about gamma m? That's the covariance of y1 plus m. That's gamma m. And for this one, if I want to derive their covariance, I will still go back to the original definition, right? So the covariance is actually can be written as expectation of y1 plus m minus the product of expectation y1 times expectation y1 plus m. Okay, I'll quickly sum up. You can just do the calculation yourself as we did here. Go back to the definition of y1 as x1 times x1 plus m. So basically, I can show this is equal to tau squared mu squared. Okay, so I omitted steps here, the algebra. So finally, you see by that theorem we just proved today, we can show that root n times Sn over n, that's the average, minus mu. minus mu squared. So that's actually the mean of xi plus 1. Yeah, so this one will actually converge in law to normal distribution with mean 0. And the variance term, or asymptotic variance term, will have two parts. One is this part, okay? So tau to the fourth plus 2 times tau squared mu squared. That's the first part. And the second part is 2 times this, right? And this is the only term in my summation, 2 times tau squared mu squared. That's it. So this is an example showing that we can actually derive the asymptotic distribution of terms like this, of summation like this. So inside the summation, every term is no longer independent, but they are still identically distributed. So as long as we can figure out the dependent structure, that is here, only this and this are dependent. And we can verify, oh yes, it's actually the M dependent sequence. So it satisfies the stationarity and M dependence. Then we can directly apply that theorem. So what's left for us is to derive the variance of every term in the summation and the needed covariance of terms in the summation. With that, we can plug them into the asymptotic variance. And for this one, we need to derive the mean, right? The expectation for each yi. That's it. So I think that's all we need for this. So this is actually, I'll just say one thing. This is the expectation of yi. So that's an example to show how we can use this theorem in practice. So once we come back to the Thursday lecture, we will show another example of the application of this theorem, and you will actually see more in your homework. So that's all for today. And if you have any questions, you can come to the office hour today.